Okay, so let's start. So the objective of these 4 blocks is to do an introduction to tensor network states. And the way I will see it is that for me it's a compression method. It's a compression method for many-body quantum systems. Many-body quantum systems. So why do I say that? Because tensor networks have a ton of various applications, and the angle I will take is this one. So just to be clear, there are other. So this is one use. So typically we are gonna. This is a way to see it is like it's like the zip for a quantum state. Another use is to compute partition functions, usually with some tensor RG. So this is a popular thing. And there are also applications in machine learning. So you will encounter them, but so I will not mention them at all. We will really be focused on the many-body quantum states. Also, before I start, I mentioned that there are 1 million references on this now. So I will give you meta. So one way could give you a meta reference, like some kind of review. So I will give you a meta reference, which is a website where you have reviews. So you have a tensor network. OK, they don't have just reviews. They have also like basic explanations of the main concept. So tensornetwork.org. This one is mostly done by my student Meyer, and there is also tensors.net mostly maintained by Glenn Evenbly, I think. And actually, I found that on the basic question, GPT-4 is fairly reliable to ask basic questions. But you have to check when it tells you who did it first, for example. OK, so that's just for the introduction. And we will do, ideally, 4 times 1 hour 30. I will give you later an outline of what we'll do during that time. But I don't want to waste more time and start right away with a sort of long introduction of what is the problem that we are trying to solve and why tensor networks have been successful at it. And then we will go deeper in all the parts I mentioned in the introduction. OK, so first, our objective is going to be compression for the many-body problem. And we have to understand what it is. What's a many-body problem is, OK? OK, so the typical problem you have, and I'm going to argue that, in a way, this is the problem of most of modern theoretical physics. You have some lattice of sites where you can have a spin or an electron, and the Hilbert space of your quantum system decomposes into a tensor product of small Hilbert spaces associated to each site. And then you have a Hamiltonian that is a sum of local terms. And this, I have just should have checked that before. Anyway, so far we'll do color later. And these local terms are typically terms acting on only a small number of sites at the same time. Now, of course, they can overlap, and that's why, if you like, this is HI, AJ. So that's why the problem is difficult and not instantly solvable. Okay, so let me give you some examples. So the first is any model of magnetism. So if you have spins, then H is equal to the tensor product over all the sides of C2, and this is C2 to the n if you have n sides. And a typical Hamiltonian, I don't know what I took as an example. Okay, this is just an example, but essentially you can have some sigma z local term plus you can have nearest neighbor term. Okay, maybe you do it also on y, I don't know. This is just to show that it's potentially quite arbitrary, but what we typically have is the local structure. And maybe you have J2, sum of now some next nearest neighbor term of whatever thing. So that's an archetypal, simple many-body problem. So this is a bit the theoretical, I mean, this is used for magnetism, but this is also the typical theoretical physicist many-body problem. It can be very concrete if you have another example are electrons in solids. And then you have typically the Hubbard model. With some hopping between fermions. Okay, these are fermion creation and annihilation operator. And sigma is spin. And this is the Hubbard model that I wrote, which is believed to be a good model for high temperature superconductivity. So probably you need to tune it a little bit to get a good model of superconductivity, but it's a model in which electrons hop on a lattice and then interact, and the fact that they interact strongly makes the model highly non-trivial and not solvable with standard tools like band theories. But also, I should say, discretizations. The last example is discretization of the standard model, so of the fundamental laws of nature. So I won't write the Hamiltonian here, but take any fundamental theory of nature, the standard model, discretize it. It's going to look like this, a Hamiltonian that is a tensor product of local factors and a local Hamiltonian. So in nature, sometimes we have things that are not local. Okay, think of 1 over x potentials or things like that. But these are usually effective description. If you go deeper, you get back to local degrees of freedom, at least in the formulations we have of physics. So this is just to argue that it's a fairly general problem, okay? Okay, and the question, I mean, the $1 million questions we have all the time for this problem is, what is the low energy physics? Or say low temperature. So that's really the question we want to ask, because at very high temperatures, these things are going to become completely classical, like all the physics that we know. We're going to be able to use even classical stat mech in some cases. So we are interested in the low temperature physics of these problems. And why is it difficult? And that's the core of the many body problem. And okay, this is a bit trivial, I know, but even in the simplest case, when the local Hilbert space is small, the smallest possible, C2, you write a generic state like this. And now you have 2 to the n complex coefficients. And that's very quickly limiting if you want to find the low energy states with direct diagonalization of the problem. So I know some of you are familiar with this problem. In some cases, we have difficulties for n small because the size of the Hilbert space is already big. Okay, if you have bosons, for example. But I would like to say that the problem is not so much the 2 here that could be a 20 or a 100. The problem is really the n here. Okay, the fact that it grows exponentially. And so a standard technique, which is exact diagonalization, which I'm going to write here. I mean, it's good to know the exact what is the state of the art. So I mean, you can try to be smart because you see that the Hamiltonian we have here is extremely sparse, so you're not going to write it as an explicit matrix. But your vector here is dense, okay, even if you're smart. Maybe you can exploit some symmetries and reduce slightly the number of parameters, but it's never going to cut the exponential growth. So even if you're smart and use sparse resolution techniques like Langshaw's, you're going to struggle with the exponential size of the Hilbert space. And as of 2018, the world record, so I'm not sure it's up to date, but by Vitek and Andreas Leuchli, was 50 spins on 10,000 cores. And I think each application of matrix vector in the Langshaw's algorithm is like 20 minutes. So it's very, very difficult. I mean, this is really, this is impressive. And they managed with clever tricks of parallelization to make it better. However, and on your laptop, you can easily do, even with dense, you can do easily 20. I think if you do Langshaw's smartly on your laptop, you can probably do 30, 35. With insane supercomputing resources, you can do 50. And also with very smart people coding it very well, you can do 50. So never, I think we can safely bet that never ever in the history of mankind will we do 100. Okay, so we can maybe at some point when I'm old, it's going to be 70, but it's not, this is a hard barrier, okay? Being smarter at coding the stuff is not going to save us. Of course, there are solutions to this. Let's mention them before mentioning the sort of modern ones, or not really the modern one, but the cool kids we're going to talk about. So one approach is perturbation theory. So in this approach, you will use, for example, for the Hubbard model here, you can use the fact that if the model is purely without U, it is exactly solvable. It's a Gaussian theory. Then you can do perturbation theories as a perturbation expansion as a function of U. But of course, you're going to be limited to small values of U if you want to be precise. Okay, then you have practical considerations. How do you compute many terms in the perturbation expansion, but also theoretical one that some domains are just not reachable in principle because it's not going to converge. Okay, so it's but it's small coupling. You have Monte Carlo, but as you know, so Monte Carlo works miraculously for problems that have a certain, that can be sampled from, and in some cases you have a sign problem. Actually, in many interesting problems, you have a sign problem, which means that Monte Carlo doesn't converge. And finally, you have, in some cases, ad hoc methods. For example, for electrons in solid, you have DMFT, which usually work very well, actually, but are approximate and non-refinable. So methods, I would say more generally, methods based on mean field. Approximate. But, okay, but what are the future solutions? I mean, many of you are familiar with one of them, I think. I say future, some of them are old, but I want to insist on the fact that they are not yet used for, are not used that much for real-world problems. Yes? No, I think you can pretty generally create configurations where you have problems in Monte Carlo even without fermions. Okay, so of course, most of you know quantum computers. That's the easy way. I'm joking, okay. Theoretically easy way to solve it. So you encode directly. Also, what I want to say is that the current solutions that people use are avoiding the fact that we can, bypassing the fact that we can't write the state by working just with something else entirely. These two other solutions really go back to the state. So you encode psi directly. And that's, of course, very smart. And you have, I think, tensor network states where you compress psi. Okay, so this is classically. Okay, some tensor network methods could be run on quantum computers, but that's putting too many things at the same time right now. Okay. Okay, so now I keep on with this sort of broad introduction. So what is the idea of compression? Well, is that you have this colossal Hilbert space, the many-body Hilbert space of exponential size, Hn, maybe with n very large. And you have your state of interest. So I'm going to argue a bit more later why I'm ultimately going to care only about the ground state, sort of because the first excited states are very close to the ground state for practical purposes. So I have the ground state of my system. It's here. It's a very complicated entangled state. Okay, it has no simple expression in the spin basis or the electron basis. And of course, optimizing, finding the best state in terms of energy over the whole Hilbert space would give me this. But I can't, so I'm going to carve spaces that I understand well. And with an increasing number of parameters, I'm going to call this guy, say, MD. D is going to be a shorthand for how big it is. Okay? If I have more and more parameters, I span a larger fraction of the Hilbert space and have more reasons to be closer. And then my hope is that if I have a good compression, I will have that the ground state is approximately equal to the argmin for all the psi in this subspace of the Hilbert space of psi h psi. OK, and let's say I don't assume it's normalized. Then by the variational principle, I will have that. OK, and if I replace here by the whole Hilbert space, of course, I get an exact statement. OK, and then I could get the first excited states by optimizing on the orthogonal of what I first found here. and iterate. Okay, that's why I would like to focus just on the.
But it should be less and less local.
Sorry?
Higher excited states typically would be less local than the ground state.
Okay, but if you stay, when I say what I care about is the ground state, maybe the first few excited states, but not an exponential number of them. So it's a it's an exponentially small corner of the Hilbert space. Even if you add the first few excited states, that's what I mean. Okay, so here, usually, then we start right away by constructing tensor network states, and I think then we don't understand the point. So I think it's good to try and build stuff with this philosophy and give naive solutions, because very frequently, actually, I see people who invent new ideas, and that's good to try new stuff. Okay, it's a philosophy that is very generic to try this. But there is a good reason people started converging on tensor network states, and so for that, it's good to try. So let me find a naive solution is to take a Hilbert space truncation. And by that, I mean a linear subspace of the Hilbert space. This space doesn't have to be a vector space. It could be something very nonlinear. But you could take something simple that is just a linear combination of terms. And in particular, okay, you could look at a state that is, I'm going to work in the spin basis, that is a sum of terms with one excitation. Okay, this is the thing creating a 1 in position, adding, okay, my spins are 0 or 1, and this is flipping 1 in the ice position. Or is it sigma minus that does this? I never know. Okay, if it's not, I could take sigma x actually. Okay, I could take x. Okay, you switch it if it's wrong. And again, and maybe you're going to have to stop at some point. At order k. Okay, so you could look at the subspace of, this is a very, very natural thing. In fact, this is, what I'm writing down here is the lattice version of Hamiltonian truncation, which is a popular scheme in field theory. You start by, you construct your Hilbert space this way, and of course, because memory is limited, you will stop at a number k that is fixed and that doesn't depend on n, or that at least you cannot grow very easily with a number of sites in your system. Okay? And the question is, does it work to do that? I mean, if it did, that would be over, okay? The question is, why doesn't it work? Why is it, or is it clear that this should not work? Okay, and the reason is basically a problem that these states that we construct this way are not extensive. So I have to say a bit what I mean by extensiveness. The low energy states of many body systems with local interactions are going to be intuitively extensive. What I mean by that is that if I write, okay, I'm going to imagine we are translation invariant here for simplicity. And as a result, that all my hi here are the same. Okay. Then, if you look at this, for example, this is going to give your energy density, and the full energy density is just the full energy, sorry, is just n times the energy density. This is true for the energy, but it typically is going to be true for everything. So if I look at the magnetization in I, let's say I call that small script s z, then the total magnetization is going to be n s z. Okay? That's clear. I mean, you can define intensive quantities sort of like this, and then you get the extensive one by summing over the system size. Okay? That's a basic property we expect in any system that is reasonably local. Okay, maybe this statement, I should say, this statement is true maybe when n is large. Okay, not. Put it all the way back up. Okay, and these types of states that I wrote down, they never verify this. So, for example, if you look at psi f that I just defined, you'll have that psi f SZ, sorry, psi f here. Smaller than k. So you can't have more spin-ups than the order here in the total system. Okay? But this is going to be much, much smaller than something that scales in n, okay? When n is large. So what that means is that you should scale the order of this expansion. You should increase the order here more or less linearly with the size of the system. And what that means in turn is that the cost is exponential. You're back to the exponential scaling that you had initially. Okay, so it's sort of a way to see it in this kind of patatoid of the Hilbert space, that you have the ground state here. I have my, like this is the space of all the psi f for a fixed k. And here, the distance between a fixed order is proportional to n. So you have to scale the order as the size of the system increases to get a good precision. And so in practice, you're never going to be precise. Okay? So of course, it can be decent for small systems, but in a way, it's a reformulation of exact diagonalization. Okay? You don't expect a better scaling than exact diagonalization. Yes?
So why is the scaling not linear here? It appears.
Yeah, but okay, the cost is not linear in k. You see, the complexity as k increases is crazy, okay, because the f has many parameters. As many parameters as k, okay? So a fix, and this is, okay, of course, I took the spin. You could say, because you made it very asymmetric, you started from 0. Okay, I could sort of start from a state that has the right average number of spin, but then I'm going to find another operator that doesn't behave extensively. Okay, so you should more or less be extensive for all operators. Yeah?
In a way, can't we say that the problem is your compression doesn't satisfy the same class of symmetry as your Hamiltonian? Your Hamiltonian is translational invariant, your compression should also be.
No, so it's not a problem of translation invariant. It's easy to make these states translation invariant at k fixed. Okay, so it's not a problem of translation invariance. It's hard to phrase it differently than a problem that it's not extensive. Like a way to, if it were electrons, the problem is that you can phrase it in terms of number of particles in the system, with this truncation, the only way you can manage is to fix the number of particles or bound the number of particles. But the number of particles increases linearly with system size, typically in your ground state. And so you'll never manage to catch this. And this complexity, I mean, of course, you can change of basis and try to find a good basis. But I would say the only basis that would work is the basis diagonalizing the Hamiltonian. And that's precisely what you don't know and what you're trying to find. Okay, so a fix, so this is, I claim it's not rigorous, that any approach based on linear subspaces where you try to take larger and larger vector spaces of the Hilbert space will encounter such issues. A fix would be, okay, this is sketchy, it's a fix that doesn't work, but a fix that, is to just exponentiate the operator we put here. I should have given it a name, sub of fi 1 sigma I plus the sum of ij. Okay, I guess you understand where this is going. Now applied to 0, 0. State defined like this from exponentials will have much better properties. There will be sort of by design, okay, I'm not claiming this really makes sense, but this would be a way to lifting typically into exponentials makes things more extensive. The issue is that then you encounter the second problem. It's totally impossible to compute with this. Okay? You can't compute anything. Sort of now, if you have some very, very complicated, so when the term is below, it's very easy to compute Hamiltonian elements between states like this. Here, take the scalar product of psi f and psi g. It's going to be very hard, okay, in general. Yeah?
It's basically what coupled cluster techniques are.
Yeah, but then you take lots of approximations. Yeah. Okay, so I'm saying without, let's say, this is your, you're right. This is used. This is because this recovers a good property. But say, exactly, you can't compute anything. So you have to, at some point, stop being fully variational. Okay, and what I should have said is here also the energy you get here is an upper bound to the true energy. So these kind of properties, if you want to get them exact with such states, are difficult.
But Antoine,
yeah.
If you want to do a computation with that kind of operator, you still need to somehow expand it, right? So
yeah, but this guy has infinitely many excitations typically.
Yeah, so you are back to the same problem. You cannot take it.
Yeah, but there could be smart ways. Maybe you could sample in some cases. Okay, just saying practically it's difficult to work with such. Okay, and of course this breaks the linear structure. I just wanted to give it as an example that this breaks linearity, and that's part of the good thing. Okay, and this was so. If I gave you a spin chain in 1990, okay, a spin chain. With some Hamiltonian, say like this, but you're in one dimension, with arbitrary terms. It was very hard to compute anything. There was no technique on the market. And in 1991, the situation changed with DMRG, density matrix renormalization group. It's by Steve White. And from one year to the next, spin chains like that were essentially numerically exactly solved. Okay, so we went from, it was impossible to get 2 digits, maybe I'm exaggerating, but like get good approximations, to essentially for typical gapped spin chains, you can get machine precision. So there was a phase transition in what you can do. And I'm just going to say very quickly what's the... Of course, the whole point is going to be much later on to understand DMRG. But now I just want to say vaguely what it is before we dig into the details. Okay, so I'm saying the philosophy of DMRG. So what I say the philosophy of, because it's not exactly DMRG that I'm presenting, and in modern terms. So it's completely anachronic. It's not. It was understood later in a way what DMRG was doing in. It was really a numerical algorithm. Okay, so what you do in DMRG is that you organize the free okay, and I will do translation invariant case, which is really anachronic because DMRG is initially not for translation invariant. But okay, I am really cheating right now, just to give an idea. And so yeah, you organize your free parameters. So okay, before my free parameters, for example, in this, there was the f, okay? You could easily store them in a computer. You have a one-dimensional array, a two-dimensional array, a k-dimensional array of potentially complex numbers. Now I organize them weirdly in two complex D times D matrices. So really, I will call them A0 and A1. So they are, it's just the way I decided to organize my free parameters. I could have vectorized it, but it turns out it's convenient. And the state I define, and right now, I mean, if you have a good intuition of why it works, you're smart, because it's not going to be very obvious. The whole point of these lectures is to explain why actually it's a good choice. Is to take the trace of a product and then okay, so that's my definition. That's my class of states that, in analogy with here, if I increase the size of these matrices, I have more parameters. And so I get a better approximation. Of course, this state is a matrix product state. That's the name. Actually, matrix product states were introduced roughly at the same time by Fanes, Nash-Tergele, and Werner. But I don't think the connection was made until much later, that in fact, DMRG was equivalent to a minimization over this class of states. Okay. DMRG was a more obscure toolbox. Maybe it helps to expand a little. Okay, so what are the coefficients? Now let me try to see what are the coefficients. Well, the first term is A0 to the power n, and this is all zeros, and then I have the trace of A1, A0, and minus 1. This is 1, 0, 0. Okay, you get it, right? Then this keeps on. And I have 2 to the n terms. But of course, these 2 to the n terms are really, really special because they are deep down parameterized by only 2 times d squared parameters. Okay, this is usually called the bond dimension. We'll see later why. Okay, so this is just, I want to flash what an MPS is before going back to more complicated, sort of more general discussions. So are there questions about the definition of the states? Yes?
The fact that we use two matrices, it's also one parameter of the method? Or it's
No. Okay, here, 2, you're right, that's a good question. So 2 is because I'm constructing a state for spin 1/2, so where it's 0 or 1. if I wanted to, if I had a qubit, this guy would go, okay, this is horrible. This guy would go to D, like this. This is the Hilbert space, local Hilbert space dimension of my problem. Okay, so that's, I mean, we see already that it's trivially extensive. Okay, no, it's not trivially, we will see, I guess. It's not obvious that you can compute anything with it, okay, so far, that expectation values are easy to compute. But I'm going to give you a few facts. Yes?
First, is this a tensor product or just a product of matrices?
So here it's the matrix product.
Okay. And
so here it's just like the usual matrix product, and then I take the trace, so it's a number.
okay.
So it gives me the coefficients in front of.
Okay. What are I1?
Sorry, they go from 0 to 1. They are the spin values here. Yeah. I should have been more precise. Okay, I did it for a spin 1/2. If we had a qubit, we would have D matrices here. But okay, in many cases, I think you can assume the physical dimension is 2, because we are really concerned with problems that become difficult as n becomes large, and not so much when the local dimension becomes large. I would say it's not. In all these MPS methods, you take the local dimensions to 10 and nothing changes, okay? It's not where the cost comes from. Yes?
And the choice of A0 and B1 is totally trivial, right?
So it is arbitrary, okay? I didn't yet tell you, actually, I didn't complete DMRG here. Of course, DMRG is now, more specifically, it's an algorithm to find the argmin. Okay, then you're going to have a psi A best, if you like, that is equal to argmin over all the A0, A1, sort of psi A, H, psi A. Okay, in principle, you could do it with gradient descent or any other iterative technique. It turns out DMRG is a particularly efficient iterative method to do that, to do this minimization. Okay, so maybe, okay, I thought I was going to clarify it later, but let me clarify it already. DMRG is an algorithm. You give it a Hamiltonian, it gives it an approximation to the ground state. Matrix product states are these states over which DMRG optimizes, okay, over which DMRG finds the minimum. So the argmin is found by DMRG. But why do I say it's anachronic? Because DMRG was just an algorithm doing stuff, and people realized later that what it was doing was minimizing over the class of MPS. Yes? Oh yeah, sorry. I'm not okay. I'm being sketchy. Let's call it A. I call A the tuple A0, A1. Actually, I call A the three-leg tensor, where this is the third leg. We'll see that later. Okay. Okay. So let me give some facts so that you're motivated. Facts. Again, no proof. The whole point is going to be to dig these facts a bit more. Okay, there is a trivial fact is that we have 2D squared parameters. And this, again, this D is arbitrary, control precisions. Typically, it can be 3, it can be a few thousand, not more, okay? It's not a parameter in the millions or trillions or 2 to the 26 or... one can show that the cost of this, okay, without guarantee for convergence, but assuming that there is no weird combinatorial stuff going on. So generically, the cost is a constant times d cubed for optimization. And the error, the local error, again, I will be more precise later. What I mean by local error, I mean local for local observables. Because as you know, when n becomes large, all states are orthogonal, basically. So it's impossible to ask that the fidelity be very good, for example. In the thermodynamic limit, it's never going to be the case. Even if you take a system with 1,000,000 spins, you have the perfect ground state, you flip one spin, you're orthogonal to the ground state. So what we ask is that local observables are reproduced very well. So if you look at the local magnetization, maybe the two-point functions, okay, that all the functions that we could measure experimentally are well approximated. Okay, so that being said, the local error is a big O of 1 over d alpha for all alpha. So it's faster than any polynomial in D. Okay. So it's super polynomial convergence, but it's not quite exponential. And what that means is that practically, okay, I should say for gapped. I will be a bit clearer later. So if you know what gapped means, you're good, and otherwise, I will say it later. And so these systems are essentially numerically, this is going to look like an oxymoron, like numerically exactly solved. That means you can, for this problem, typically reach machine precision. So it's common in papers that some papers for a spin chain that is gapped, people refer to DMRG results as exact results, even though, because there are such good guarantees. This is 1D. Then if you go to the kind of generalization to 2D, then it's only getting competitive. But this is very recent. And in 3D, it's too expensive. Okay, by 2D, 3D, I mean, is your many-body system a chain? Is it living on a sheet, or is it 3D? Okay. So there is a big, big, big difference with dimensionality. I would say conceptually, everything looks the same. Then what happens in that is these larger dimensions, the cost for optimization become much, much worse polynomials in D. And so even though you think the convergence should still be very favorable, you struggle to enter in the scaling regime. Okay? Because a polynomial with a power 10 or is for all practical purposes like an exponential, even though it's polynomial. Like actually, the field, it's often mentioned, you know, when we say something polynomial is feasible, it's because we don't expect that very, very large exponents happen for polynomial algorithms. Tensor networks are a domain in which you see very, very large powers appearing, especially for this 3D algorithm, that make polynomial algorithms not usable. Okay, so that was my super long introduction to I mean, the objective is going to be to understand this, mostly the 1D. But I will start, my idea is to start from something more general, so explain the general philosophy of tensor networks in arbitrary dimensions, and then specialize back to MPS. Because I think the philosophy is mostly independent of the dimension. Then what is very specific to the dimension is the algorithm to optimize these states. And so for the algorithms, which we will probably not do today at all, we will do next time, then we will do only one dimension. Okay, because the algorithms in 2D and 3D are essentially research problems right now. There are things working, but it's not super, it's not easy to use. Like it's, okay, so outline. So I will talk about the area law a lot, which is, how to say it? It's a requirement that I haven't mentioned yet for a good variational class. Okay, now we understand this means a subspace on which you optimize. Then we're going to construct tensor network states based on this intuition, and we're going to use, to do that, PEPs. Okay, so that's the, I was going to say it's the modern way to construct them, but it's from 2004, but it's more modern than DMRG. And then we're going to specialize to 1D with MPS. And what's good is that we can see, say a lot, so we're going to give examples. Why it's good? So the explanation of why it's good is going to be partly intuitive because the actual proofs of how you get this 1 over d alpha are pretty technical. Then how to compute with MPS in principle. And if I go fast enough, we will see at the end MPS in the wild. So MPS is appearing in nature, like sort of naturally, and very artificially, but say in experiments. Okay, and next time, so by next time I mean next week, we'll see algorithms and extensions. So what I mean by algorithm, so we're going to work with MPS, but we are always going to assume at the end that, yeah, there should be something to be able to do this, okay? Once I know how to compute the expectation value of the Hamiltonian, I could do some gradient descent or something smarter. And this gradient descent or something smarter is for another time. Okay. Any more questions so far? Yes?
So in bigger dimension, is it only the dependence in big D that is getting worse? Also the value of D that you have to take dependence with n?
That's a good point. So okay, for a gapped system, D doesn't scale with n. Okay, so you can take even n to infinity first, and then only increase D. So that's not the problem. The problem in more dimensions is that computing this here, that you need to then do the optimization, is not exact. You are calling a routine. And this routine you are calling at every step to compute this. Imagine you do a gradient descent to optimize this. At each step, you're going to compute the function, its gradient. Each computation of this function and its gradient has the cost of a full DMRG routine, a full optimization in 1 dimension less. Okay? So the way to do 2D is at each step of your sort of gradient descent, you have a full 1D you solve a full 1D problem. Okay? Sometimes it will be fancy. People say it's a holographic method because you reduce the dimension. But every time you reduce the dimension by 1, you pay the price of each elementary step of your process becomes a full optimization in 1 dimension lower. Okay. Okay, I keep on then. Okay, now I want to start. So variational methods and area law. Okay, so I recall our objective is to write the ground state as argmin. There was something else. So I skipped something, but it's okay. That's what we want to do. And what we need, I recall. So I'm now phrasing the problem a bit more generally. We need expectation values of local operators to be computable. Okay, I insist because it's possible to have a very explicit expression for psi such that you cannot compute any observables with it. Okay, or that the only way to compute observables is to sample. So certainly you want that this is computable for states in your manifold. You want it to be extensive. And sort of what we mean is that the error at fixed D is independent of n. So that you don't need to scale, or maybe it's just linear, or you don't have to scale exponentially your number of parameters as the system size increases to keep the same error. And of course, we're going to need, if it's going to work, we need some, it needs to be adapted to low energy states. Okay, and that's sort of the secret sauce, okay, because in general,
What does it mean?
it doesn't mean anything right now, okay? This is where I have to do some talking, okay? So in general, a compression method should not be able to compress everything, okay? Because there are 2 to the n states in the Hilbert space. To represent a generic state, I need 2 to the n parameters, okay? Otherwise, I cheated somehow, okay? So now this is the usual analogy we take is that of images and image compression. You can compress images because a picture of a cat or of a table doesn't look at all like random pixels. A picture of a cat is highly structured, there's lots of things special to it, and so wavelet encoding is very efficient. Or if you want to do some labeling, convolutional neural networks are very efficient because they sort of take the structure in the picture to be more efficient. So here, the states we have and we want are low energy states. They are not arbitrary states of the Hamiltonian. If they were arbitrary states of the Hamiltonian, there would be no hope. And then probably the only way would be a quantum computer, okay? If we have any hope to do something, they have to be special. And indeed, they are very special, but we need to understand what makes them special. Sort of what is the catness or the tableness of these low energy states of local Hamiltonian. And this is the fact that they are much less entangled than you would expect. So they are still entangled, okay? They are not product states. They can have sort of a lot of entanglement, but they don't have the maximum amount of entanglement. In fact, they have much less. Okay, so this is objective. Now I'm gonna discuss a technicality just because I don't want to say things that are completely wrong. So we have to be careful that in this many body problem, you have 2 cases, and one is slightly more difficult than the other. And so I want to be clear. The easy case, where things are much better understood, is if you have a gapped Hamiltonian. What a gap Hamiltonian means is that if you look at your energies, you have the ground state energy, E0, and then you have E1, and then a ton of energies are going to accumulate on top of E1, and here you have a gap, delta. And this gap doesn't shrink when n increases. Okay, so if you like, E0 minus E1 is a no of 1 as a function of n. Of course, there is a gapless case. So that, for example, corresponds to critical systems, where you have E0 here. And I mean, the accumulation of states starts directly at E0. And so E1 is here. And E0 minus E1 goes to 0 when n goes to infinity. So I'm not talking of the ground state being degenerate. Okay, this is a different problem, having a degenerate ground state. In a way, it's manageable with tensor network states, but I'm not going to talk about it. I'm always assuming the ground state is not degenerate. But then the main question that will determine the physics is whether or not it's gapped. And if it's gapped, correlation functions decay exponentially, whereas here usually only polynomially, only power law, and so it's easier. Okay, so statements I will make depend on this, but I will try to tell you when it's valid for both, or in a way, gapless systems are still manageable with tensor networks, but the things are less nice. Okay, that's very unclear so far, but okay. Okay, and so because I should. That's just a technical aparté, if you like. Now I go to the area law. Maybe I should have said that just after the area law. So now consider a lattice. That's my lattice. So the area law is something weird that was first mentioned in the context of black holes, where it became something fascinating for people, but I find that the application in condensed matter is much more powerful. Okay, this is the lattice, and okay, I'm being sketchy, but okay, each intersection is my is a lattice site with this local Hilbert space, and I have on the lattice, say even 0. I have a state on this lattice. And now I take a certain region. I get a certain region. That can be whatever, but okay, it has to be smooth enough. If you take it fractal in the continuum limit, it's not going to be correct. Okay, so you are nice. You don't try to trick the statements. It's a region R, and it has a boundary that I call dr. And now we consider the entanglement entropy of R, sort of with the rest. So you have like the von Neumann entropy, which is minus trace of rho R log rho R. Or you have, actually, it's also going to work for the Rényi entropies. If you like, it's a generalization of log Okay, so I didn't say what rho R is. Rho R is just a trace over all the sites. Okay, I'm being sketchy, but that all the factors that are outside of the region of the Hilbert space of the state. Okay, if you already know some quantum information, I mean, this is just the definition of the entanglement entropy and the Rényi entropies. And the first thing to look at is that there are two cases. Now I'm going to do random pixels, okay? I'm trying to understand the equivalent of random pixels. The equivalent of random pixels for me is a psi that is random. It's sort of uniformly. If you want to be careful, sort of a way to define a psi that is really random is to you sample a random unitary with the Haar measure. Okay, the uniform measure is very well defined over the unitary group, so you can sample a random unitary and you apply it to whatever state says 0. Okay. So if this is sampled, what I mean is that this is sampled with the Haar measure. If you don't know that Haar measure business, just trust me that it's possible to define uniform random states and that there is no weird business, okay? And what you see in that case is that SR, whether you have an alpha or not, is proportional to the volume of R. Okay, so here it's the area in this drawing, so that's going to be very misleading, but the volume of R. That's the first thing. Now you take 2, you take psi, a low energy. Okay, let's not be fancy. Let's take the ground state of H that is local. Again, by local, I mean like before, that it's a sum of HI that don't have different lattice sites torque arbitrarily far away. I'm OK with next nearest neighbor, next nearest neighbor, next nearest neighbor, but it has to stop at some point. Of H local, and here, this is where we need gapped. Then SR scales with the, let's say it like that, the volume of the boundary, which is called usually the area of R. But this is, okay, this is the area in 3D, but it's the perimeter on the drawing, okay? Okay, so here it expands infinitely.
So you're taking the thermodynamic limit.
I mean the thermodynamic limit. My lattice is infinite, and now I'm growing the size of this region. Okay. I can do it infinitely because then this extends to infinity, okay? And I look at how it scales. Sorry, this is when R. Yeah, this thing is to say. This is when R is large, when you start to take big regions such that the weird peculiarities of the lattice don't matter anymore.
So the R measure is something like defined for
okay.
manifold somehow.
You mean here if I wanted to take the uniform measure?
Yeah,
I would have to take n very large, but not. I have to take n huge first, the number of total sites, and then grow R such that it's still very small compared to n, but still big compared to the lattice scale.
And it looks continuous.
Yes. So I'm being sketchy with limits, but this can be made fairly well. Okay. So this you require gapped. Why? What's the problem? If you're gapless, you can have logarithmic correction. So it's not necessary, but you can have here. You can have time log of vol of R. So in this, you can. It's not necessarily the case in 2D in particular. But say in 1D, in one dimension, the boundary of the region has finite size. It's 2. Okay. Okay, I should say there are constants in front. Okay, like this is like it's a big O of this. Yeah. So where the difference between gapped and gapless is really dramatic is in 1D, because in 1D the boundary is 1, it doesn't grow with R, and so this logarithmic correction looks really big in comparison, whereas what is growing as n already.
And this, I guess, is related to the fact that for gapless theories, so they are long range.
Yeah, exactly. It's because of the power law decay of correlations. Yes?
I have a doubt. How is that the entanglement entropy is growing, but I consider a system that's much bigger?
I will explain, I think, in a few seconds. Okay, it's sort of here, I'm sure, maybe I've been a bit sketchy. You have two limits. So first, you take the lattice almost infinite, and now you start growing your region, such that, but it will never see the boundaries. The region, even if I take the region large, it's still much smaller than the full lattice.
Yeah, but I'm thinking, while I'm considering more information, how is the entanglement entanglement entropy growing?
The question is, how entangled is it with the rest? So if you take something bigger, it has more ways to be entangled with what remains. We'll see, but we'll see especially how it's different in the two cases. Why, in a way, the volume law is intuitive. But let me, I have to be clear about the status here. So in 1D, and for the Feynman entropy, and the gapped case, okay, this was proved by Hastings, by Matt Hastings, who was then at Los Alamos, now at Microsoft, so it was in 2007. And it's also proved, so I don't know if it's, I think at least this is where I get the results. Yish and Huang in 2014 for the Rényi entropy. Still in 1D, okay? And I should say, okay, insist in more than 1D. This is a common expectation / folklore / we've tested it numerically and it always works, and intuitively that should be the case, but okay, there is no proof. No proof that this holds. But it's a reasonable assumption to, I mean, you can work with this assumption and see if it works, okay? It's not. Okay, and this is where I want to give the intuitive picture. So this is going to answer your question of why does it get more entangled in a way. So what the area law, so the thing to understand is the area law looks like a very small reduction, an algebraic reduction in entanglement. Something that's not so crazy in a way. But it's much more than that. So because of the area law, it means that entanglement is local. And so that's a big difference. That's an exponential reduction in complexity, not just a polynomial one, as you could think from this change of scaling. So I'm being sketchy right now. I will make it more precise. So this is my lattice. I'm going to draw a volume law. Now I'm going to be super sketchy. I'm going to imagine all the entanglement in nature takes the form of bell pairs. That's not true. You can get weird stuff. But let's now assume that all entanglement in nature is bell pairs. If I draw stuff in blue, you see anything or not at all? Let's say I do this. No, it's all right?
We'll see the difference with the white.
Yeah, OK. I will, at the break, I will get better chalks, OK? So, for example, I can have a bell pair, connecting these two sides. And what the volume law tells you is that the bell pairs are sprinkled randomly. So there is no notion of locality. OK, this one goes to infinity. Maybe this one, by chance, is short, but OK, this one goes here. That's sort of the pattern of entanglement in a volume law state. A basic, OK, what I do when I draw this, I mean, say, OK, I'm not even normalizing or anything. I imagine an entangled state between here and here. Between the 2 points here. So here I have a spin, and they are in this global state that's entangled.
But in your high-dimensional vector space, what is
But then it's tensor with the rest, OK?
okay.
But each pair of spin that is written like this, I should fill everything with pairs here if I was really doing. But it's too hard, OK? So this is just a pattern. Let's say the one that I didn't connect, they are just in a product state with the rest, in some state. OK. this is just to try to give a sketch. This is how an area law looks like pictorially, if you, a volume law looks like. And indeed, if I grow sort of with overwhelming probability, all the states inside my region are entangled with outside, okay? Because the range is so long on entanglement. There is no locality notion for entanglement for a random state. That's why when I grow the region, essentially I just access more pairs connecting with the rest, and so that grows with the volume. So the fact that it grows with the area is super special. And what that means is that entanglement has to be more or less short range. So not necessarily one lattice size, but maybe two. But OK, I mean, I will really need to take colors later. OK, and so then I will still try this kind of purple thing. When you grow a region like this, actually this one is visible, no? You understand that it grows with volume. And here, clearly the number of pairs you're going to cut is proportional to this perimeter here, in that case. OK, because it's short range. So the ones that are inside are most likely connected with stuff inside. And the only pairs that matter are the pairs that are in some region around the boundary. So this implies locality of entanglement. OK, this is not rigorous what I'm saying here. It turns out that it works. It could be entangled in super weird ways, probably, that such that the area law is true, but it's not this way, OK? But entanglement is fairly short-ranged. So I just want to say, you see, really, it's a big, big reduction in complexity, even though it looks like, I mean, let's say if you're in 3D, you feel like you just go from a cube to a square. It looks like a small reduction. Just want to argue it's a big reduction. OK, actually, I have. Now we're going to start constructing tensor network states based on these insights. But I think, OK, before starting this big block, it's probably a good time to stop and take maybe a few questions before the break. I don't know, we can have a break of 15 minutes. I don't know if there are interrogations. So I know it's quite slow, OK, but now at least we understand more or less the background, and we'll be able to construct with some intuition of why we construct the stuff. Okay. Yeah.
Are the proofs in 1D like accessible and understandable within relativity?
Yeah. I mean the papers by Hastings, and you can follow them, but they are technical in a way. Like it's I will give some intuition for the result. Not so much of. I will show the result, another result, which is assuming you have the area law, show in a sketchy way that tensor networks are a good approximation. The other side is prove that if you have a gapped system, you get the area law. And actually, the intuition from Hastings is not so obvious. I mean, the argument is roughly that I sketch in very, very broad term what's the intuition. The intuition is because the system is gapped, write it in imaginary time, and you will evolution, you will see that correlation functions decay exponentially. So there is exponential decay of correlations in time for a gapped system. That's a direct consequence of the gap. Now, if the system were a discretized field theory, you would expect that this decay in time gives a decay in space. But Hastings shows that, okay, the theory is not at all a field theory. It's not at all invariant by swapping space and time. But still, this intuition is correct. And so if you decay exponentially in time, you decay exponentially in space. So if you take correlation functions in the ground state, they also decay exponentially. And then he shows that if you decay exponentially, if the correlation functions for local observables decay exponentially for all reasonable local observables, it shows that there isn't much entanglement that supports this. I mean, that's hyper sketchy, okay? And then this is tricky to prove it.
And so what breaks into D? Like, why is it hard into D and not in 1D to prove it?
That's a good point. That's a good point. The general statement is that everything is difficult in 2D. Yeah, in 2D, I don't know.
So in the 1D proof, what was time and what was space, since it was 1D?
No, you have.
You mean
You have 1D in space. In space, okay. Here, when I say 1D, I always mean 1D in space. It's 1 plus 1 in quantum field theory terms. Yeah. Yeah. What is tricky is 2 plus 1 and 3 plus 1. Numerically, at least, and at least actually also theoretically. Okay, so then let's take, I don't know, 15-minute break, no, so that we have time. So